Greetings and welcome back. We will be today looking at further reactions of alkenes. We've already seen that we could take an alkene and we could add an H and an OH, and we could do that Markov-Nikov and anti-Markov-Nikov. And we've already seen how we could add an H and an X, and we could do that Markov-Nikov and anti-Markov-Nikov. Today we'll be looking at how to kind of mix and match, how to add an X and an OH, and also how to add two X's at the same time. We will start off with how to add on X2, which is to say how to add X and X. These are halogens, of course, so this could be a Cl and a Cl or a Br and a Br. So starting off with this molecule right here, just use a CH3 attached to an alkene, and we will use Br2, so Br-Br. The reactivity of Br-Br, or Br2, is that it's actually quite electrophilic. It's a little weird, but think about it this way. The reactivity of a Br is that it's a leaving group, because it wants to take the electrons it's sharing and go become Br-. But Br can't pull electrons away from Br, because both of these guys have the exact same electronegativity. Likewise, the bromine on the left wants to leave the one on the right and take the electrons with it. So they both want to take these electrons and leave. But neither of them can win. So think about kind of two really strong kids playing tug-of-war. No one's going to win. Essentially, they're both just end up grumpy. And so what they would both like is to have some new electrons from some other source so they can just let go of that rope. The bromine on the left would like some new electrons so that the bromine on the right can just take these and leave. And therefore, each of these guys is a leaving group, and therefore each of these guys is an electrophile. So, electrons in a pi bond are attracted to electrophiles. But, as we've actually seen a number of times before, you could get an intermediate with a C plus and a Br attached, and it would look like this. Again, just like the last video, don't write this down because it's not actually going to happen. But we would expect to see something like this as our intermediate. Except that C plus is really, really unstable, and therefore this newly added bromine could just share electrons with it. So these things happen at the same time, and you actually never get that. So instead what happens is the pi bond is shared with one of these bromines, while the bromines shares back with that carbon. We end up with a triangle. And because that halogen is making two bonds instead of one, and this is the only time you'll ever see that craziness happen, the halogen would have a plus charge. And if you've been paying attention in class over the last several weeks, you know that anytime we form a triangle with a plus charge, which we have done several times in the past, let's remember that we've done that with an OH plus, we've done that with a mercury plus, and every single one of these times, what happened is a nucleophile came in and attacked one of those carbons, and it would always attack the carbon with more carbons attached. Because, just like an SN1 reaction, the leaving group wants to leave, but it's easier to leave the side with more carbons, because it's easier to leave the side with more electrons. And therefore, your nucleophile attacks the side with more electrons. The only nucleophile that we have hanging around in this case would be Br minus. And so the mechanism would be that our other Br minus that we just kicked off would attack that carbon, kicking that leaving group off and giving us a brand new product that looks like this. CH3, CH, and we would have a bromine down here, and the bromine that just left would be still attached up top. So in terms of regiochemistry, which is to say what goes on which side? Well, bromines go on both sides, so it doesn't matter. This is neither Markov-Nikov nor anti-Markov-Nikov addition, or really anything like that. But we can tell that from a stereochemistry point of view, the new bromine and the new bromine came in on different faces. Because we formed this triangle, which had to just be on the top, then our new guy would come in from the opposite side in order to do an SN2 reaction and kick that off. So those two bromines come in on opposite faces. All right, let's try that really quickly. So we could also do this reaction with an alkyne. And when it comes to alkynes, we just have 2 pi bonds to add to. And so we would have to add excess X2, so let's just do Cl2 in this case. And what would happen is you'd add a Cl to both sides, but then since you have 2 pi bonds, you'd do it twice. Then we would end up with 2 Cls on each side. And that would be the reaction if you did this to an alkyne. So, in essence, we're just adding to a pi bond. Since we had 1 pi bond up here, we added bromine on twice. Since we have 2 pi bonds here, we add bromine or chlorine on 4 times. And that's how this works. One thing to be aware of is that in both of these cases, if you have a different nucleophile hanging around, it could possibly do this attack instead. So whenever we do this reaction, we have to be very careful with our solvent. We have to add a solvent that doesn't have any nucleophile. So oftentimes when we do this, for our choice in solvent, we will use carbon tetrachloride, CCl4, or dichloromethane, just CH2Cl2, or CHCl3, which is chloroform. None of those guys are nucleophilic, and therefore they would be perfectly fine solvents to add that wouldn't interfere with this possible nucleophilic attack. But what happens if you use something like water? I'm glad you asked. So I'm going to shift both of these reactions up here, except I'm going to leave the solvent warning really big. So let's think about what happens if we ignore that qualification of using a non-nucleophilic solvent, and instead we add a different solvent. Alright, so let's go back and use the exact same starting material. But instead of using just Br2 in something like chloroform, we're going to add Br2 in water. So Br2 is still Br-Br, and both of those bromines are electrophiles, and so they can react with an alkene. Water, on the other hand, is a weak nucleophile, but it certainly isn't an electrophile, and therefore water can't react with the alkene, and so we have no danger of other reactions with the alkene. But what happens is the bromine accepts electrons from the pi bond, kicks the bromide off, and at the same time the bromine comes back and shares electrons to make that crazy unstable triangle. Note that even though that triangle is really unstable, the only reason it forms is that it's more stable still than a C+. Alright, so we have a really strong electrophile down here, specifically on this side, because that bromine is pulling electrons away. And therefore, any nucleophile will do to attack that spot. We do have one good nucleophile hanging out, which is Br-. And we would like to think that that Br- would just reach in there and attack. And it possibly could, except that this is in water. And when you do a reaction in water with water as your solvent, you might have one good nucleophile floating around, but you have thousands and thousands and thousands of waters. And because this electrophile is such a strong electrophile, it doesn't really care how strong your nucleophile is, it just needs one to get in there and react right away. So what's more likely to happen, and what we see happen in this case, is that the water will be your nucleophile instead. It'll just kick off there. And so the result of this product, or the result of this reaction, is that we would have our OH down here. It would actually be an OH2+, but deprotonation will happen in a second. And your Br on this side. And so again, we have plenty of water hanging around. So we're going to do a deprotonation to make that O neutral. This is something you should be very familiar with at this point. And so we will end up with a new OH attached and a new Br attached. There are two considerations here. One is that the OH always goes to the side with more carbons, and the Br will always be on the side with more H's. Markovnikov doesn't really have a rule about that, but it is Regio's chemistry. It is Regio specific. So just like Markovnikov addition, which is technically that the H goes on the side with more H's, we do have a rule to follow here, but we're not adding on any H's, so we can't really use his rule. But the bromine goes on the side with more hydrogens, and the OH goes on the side with less hydrogens. The other thing to notice is, just like up here when we added 2 bromines on, when we add the water it does a backside attack. So our bromine, if it's up, the water will come in from below. And so we will always have that Br and that OH on opposite faces. And this is called anti-addition as opposed to syn addition. In syn addition, those two additions happen on the same face. And these are both anti-additions because the two new additions occur on opposite faces every time. All right, thank you very much. Let's try another question. And please bring any questions that you have to class. Thanks.